All right, there's one more thing I want to talk about. Well, actually, let me just mention another device which we're not going to do anything with in this class, called the inductor. It's drawn as a coil of wire because a coil of wire is an inductor. Basically, when current flows through a coil, you get a magnetic field. If you try and stop the current flowing, the magnetic field resists that. That is an inductor. It has a inductance, L, and has a voltage across it. It has a current through it. So VI, well, II, let's just use L for inductance. And the thing that's interesting about inductors is that the voltage across it is equal to the inductance times the change in current with respect to time. That's the opposite of a capacitor. Capacitor resists voltage changes, right? You need infinite current to get an instantaneous change. Here, the voltage is a function of the change in current. So you can't get an instantaneous voltage change because that would require an instantaneous current change. So an inductor resists changes in current. Capacitors resist changes in voltage. We don't use inductors, and the reason is it turns out capacitors work better. They have fewer errors at the frequencies we're using them. At higher frequencies, you can't make capacitors small enough that they're very useful, so you use inductors there. But it's worth knowing about inductors. And inductance exists in any wire, but the more it has coils in it, the stronger its inductance, which, by the way, is in something called Henry's. All right. Why did I talk about that? Well, because there's an application of capacitors we need to talk about. When you build your circuits, you're going to power it from some supply. You know, there's going to be our V supply, and we're going to run it over to our circuit. Oh, sorry. Let's draw. And, you know, we're going to supply some current into our circuit. That same current is going to come out of our circuit. And we are making the assumption that whatever voltage we set at Vs is the voltage at our circuit. In fact, we expect our voltage to be absolutely stable. I mean, you know, it's like earthquakes. You know, the worst thing about an earthquake, which I luckily have not been in, is there's nothing stable anymore. I mean, we're so used to the earth being the thing that's not moving. And when it moves, it's very upsetting. Well, as an engineer, when your voltage ground moves, it's very upsetting because ground is zero, and if it moves, zero isn't a reference anymore, and everything else is changing. And suddenly, you know, if this voltage is supposed to represent temperature and ground is changing, does that mean that the temperature has changed but the voltage is constant? It's really frustrating if your voltage isn't very stable. Well, that shouldn't be a problem. We're using really good laboratory power supplies. They put out a really fixed voltage. Well, but there is a problem. We're connecting it up with wires, and wires have resistance. I mean, I know I've claimed up to now there's zero resistance, but, you know, the reality is wires have some small resistance. You know, it might be milliohms. Maybe that's no big deal. But suppose that our current, supply current, changes, which, by the way, is always true. You know, our circuits are doing different things. They take different amounts of current. Well, whenever they change, that means the voltage at our circuit is going to change a little bit because there's a voltage drop across that resistor, meaning this voltage is lower. There's a voltage drop on the ground path. This voltage is a little bit higher, means that the voltages change a little bit. But it's actually worse than that. These wires also have inductance, which you just learned about. And the thing you learned is when there's a change in current, there's a change in voltage across the inductor. So if our circuit is sort of turning on and off the amount of current it's using, it's causing a voltage drop to appear because you have a dI/dt across this inductance. Once again, this inductance is very small, but it can be enough to cause your circuit not to work. I mean, if you've got a circuit where 0 to 10 volts is temperature, and you want to be able to measure temperature to like a millidegree, well, you know, a millidegree is now 10 millivolts. And if the current changes enough to cause a 10 millivolt, you've now lost your error margin. So how can we fix that? We want this voltage to be stable, but we've got to connect it up with wires. Wires have inductance, wires have resistance. What element do we know that resists changes in voltage? Yeah, we can use a capacitor to fix this problem. What we can do is we can put a capacitor here between the power supply and ground. This is called a bypass cap. Sometimes it's called a decoupling cap. It decouples noise on the power supply line. By the way, this change in power supply we call noise because it's unwanted. So if we put a bypass cap in, we can slow down changes. I mean, we can't get a very fast dV/dt because there has to be some current going in or out of that capacitor to cause its voltage to change. And I'm going to show you that. Let's go over here. So let's look at the test circuit. So I built a circuit to show you the value of bypassing. There's a 555 that's just generating an on-off signal at about a megahertz. It's going into a digital circuit that's just counting. It's just counting in binary 0, 1, 2, 3, 4, 5. And the outputs of that are either sinking current. These outputs at the bottom are either 0 or 5 volts. So either 0 or 5 milliamps is flowing through these resistors. So I got 3 resistors. Anywhere between 0 and 15 milliamps is going on and off, on and off. 15 milliamps isn't a lot. But this is being supplied by a 5-volt supply over here through some wires. And let's take a look at the 5-volt supply. I've got my scope connected up just to the power supply. It's ground and power supply. You'd expect it to be 5 volts. Where did additional sources go? So when it comes up, there's 2 things on the screen. The blue up there, and I'm just going to stop it because it's a little easier to see. The blue, this is 1 volt per division, 1, 2, 3, 4. That's the 5-volt supply at 1 volt per division. Those spikes, those are the things I don't want. Those aren't supposed to be there. That's noise. And they're huge. I mean, they're basically almost a volt peak to peak. In the middle, what I've done is I've switched my scope to an AC position, which puts a capacitor and gets rid of the DC value, so I can blow up AC signals. And this is 500 millivolts per division. And you can see this spike is 1, 2, 3, 1.5 volts. That's really ugly. So what I'm going to do is I'm going to put 1 capacitor between power and ground. 1 capacitor, I think it's a 0.1, it's a 0.1 microfarad, called a bypass cap or decoupling cap. And now, in order for that to happen, we would have to have the capacitor change at a very fast rate. That's why I picked 1.3 megahertz. You can see that's really nice. And in fact, if I go up by a factor of 10, this is now, it's 50 millivolts. Whoops. Come on, scope, be good. All right, so that's 50 millivolts per division. So first of all, on the 5-volt line, it now looks pretty good. It's pretty close to being 5 volts. And here, I now have a 1, 2, 3, maybe that's 150 millivolts rather than 1.5 volts. I fixed this circuit by a factor of 10 with 1 bypass cap. So what's the takeaway here is you should always bypass your circuit. It turns out if your circuit doesn't work because the power supply isn't being stable, it's really, really hard to troubleshoot. The result is if you call me over and your circuit isn't working and I don't see any bypass caps, I will walk away and then you'll write bad things about me in my evaluation. So maybe I'll say something like, you should put some bypass caps in there. So let's take a look at how I build circuits. So here is a circuit that we're going to use for demonstration in just a second. I put my ground here and here, and then I put 5 volts here and here. Connect them at both ends, at least the ground. Because remember, inductance and resistance in the lines feeding your circuit. The more connections you have, the less the resistance, the less the inductance. So I will always insist that if you have grounds top and bottom, which I like, that you have a ground on both ends, a line on both ends connecting them up. But I do it with the 5 volt too. And once you build your final projects, I've seen people build final projects with like 12 breadboards with one little wire connecting each one. And by the time the 5 volt gets to the last one, it's like 3 volts. All right. What I have here, these are my bypass caps. The size doesn't matter. 0.01, 0.1, anything you got. In fact, we have a drawer in the parts cabinet that says bypass caps, and it's just all of our bypass. People who didn't want to sort capacitors, we threw them in there because it doesn't make a difference. You know, I put one in about every inch or so. I put maybe one electrolytic. Electrolytics are not very good. They're slow, so they don't respond quickly. But it's good to have one maybe. So I've got one electrolytic, make sure plus goes to the higher voltage. And then I have some ceramic bypass caps. And you know, when I start a project, the first thing I do is lay out my power buses, put in some bypass caps, and then I don't have to worry about it. The worst thing is don't put any bypass caps, and then your circuit doesn't work, and then, you know, you put in bypass caps, maybe it fixes it, maybe it doesn't. So always put in bypass caps from now on.